Hello everyone, this is Comp 150, Lecture 9. So here's the plan for today. We're going to talk about several algorithms. We're going to talk about find and count algorithm. We're going to talk about binary search. Binary search is a very important concept. And then we'll see three sorting algorithms. Okay, so that's the plan for today. And we'll start, I think, with find and count. These are sort of the easiest ones. I need to open my project. Open Lecture 9. Okay. So let's say I have a list of numbers and here's my goal. The function find, here's what it needs to do. It gets the list, A. Okay, so this is my list of numbers. It gets an element. And my goal is to find an index that contains the number 9. Okay, so if we run this example, so it will say, okay, so print info is just a function that sort of prints the information. Okay, so the number 9 is in list in position 2. Yeah, that's correct. All right. And for example, number 10 is not in the list. So, okay, so find either returns the index or some special number that indicates the number is not in the list. And I also want to write a function called count. So count one counts how many times I have one in the list. So I have one here, one, one, one. I have 4 times and it says the number 1 appears 4 times. Okay, so let's do these these two functions. Okay, so how do we do find? So that's pretty straightforward, I think. So let's say n is the length of the list. And then I say, I have just a for loop that says for I in range n, if list in position I is the key, is the number that I'm looking for, then return I, return this index. And otherwise, well, return -1. Okay, so -1 indicates it's not in the list. Okay, and pretty straightforward. I think you should all be able to do it. And there is another way to do it, in fact, and it's called list actually has the standard method called index, the standard function called index that returns the first index that contains this key. And if if the key is not in the list, this function returns an error. So we should first check if key is in the list, then return the index, and otherwise return -1. So these are two alternative definitions. This is more explicit. Although in real life, I would just, I would simply use this one. Okay, so this is find. How do we do count? Well, count is, also pretty straightforward. We set counter to be 0. And then for each element in the list, if the element is equal to the key, we increase the counter and we return the count. So notice a difference. I think this difference is sort of important. When talking about find, we actually needed to create a range n, right? We need to create range of n numbers for the for loop to y because we want to know what's the index. On the other hand, when we just want to count how many elements we have in the list, we don't need to do that. So we simply go over all elements in the list. So I think, this would, if I were to use for I in range n here, it would not be as pretty in the sense that it sort of suggests that I need the index for something. And here I really don't need the index. I just need to look at the elements. I don't care about the order. Okay. So this is our first example, find and count. Okay. Here is our second example called binary search. And here's the idea. So for binary search, suppose just for a second that the list A is sorted. If the list is sorted, then it turns out we can implement the search algorithm that will be much faster than simply going over the elements one by one. So for example, here the list is sorted. Okay, and let's say we're looking for the number 10 in this list. So before I actually show you the algorithm, so here is what I would like to do. So I look at all my numbers in the list. and I look somewhere in the middle. So here the middle is 71. Okay, so it sits somewhere between, right? I have 2, 4, 7 numbers on the left, and I have 7 numbers on the right. So 71 is exactly in the middle. So here's an observation. So I look at this 71, and where will 10 sit if 70, if the list is sorted? Should it sit on the left of 71 or on the right? It should sit on the left. Why? Because 10 is smaller than 71. So all these numbers, I can throw them away. And what happens is effectively by only making one check, right? Only one if statement, I get rid of half of the list. So I'm remaining only with this half of the list. Okay, now let's look in the middle again. So maybe I'm looking at 9. Okay, so is 9 smaller than 10 or greater than 10? So 9 is smaller than 10, which means I can get rid of this entire part. And what am I left with? 10, 11, 12. Maybe I'll look at, I don't know, 11 or 12 then, and I'll throw this away. Sort of when I get to small numbers, then, I kind of can just do brute force. But the idea is, let's try this example again. The idea is every time you look in the middle and you ask the midpoint, is it greater than the number we're looking for, or is it smaller? If it's smaller in this case, I should go right. So I'm left with this sublist. In one operation, I got rid of half of the list. Then I'm looking at 164. 164 is too large, right? It's more than 80. So I'm going to throw away all these numbers and I'm left with only with these three. Then I'll maybe look at 100 and I'll throw away the 111. And then I'll look at 71. I have only one element left. It's not 80, so I declare not found. No, let me delete all this. Okay, so that's the idea about binary search. So maybe one example that people usually mention here is suppose you have a dictionary, so a dictionary means just a bunch of words there, but they're in alphabetic order. That's convenient. And you are looking for a certain word, like octopus or something. So you don't start from the first page, A and then B and then C. This is not how you look up a word in a dictionary. You check somewhere in the middle, and maybe you open the middle at letter K or something. So does O come after K or before K? So if I remember correctly, O comes after K, which means I only need to look from K onwards. I don't need to look at half of the pages from A up to K. And then I only need to look from K up to Z. Okay. So maybe I choose a page somewhere in the middle again, and I get a P. So is octopus before P or after P? Okay, so KLMNO P. So O comes before P. So it means I can throw away everything from P onwards. So I'm only left with letters from K up to P. So basically each time I divide my entire book into one half and then 1/4 and then 1/8 and so on. That's the idea. Okay, so let's try to implement this. So we get the list and we get the key. And how are we going to make this division? I'm going to say that start is equal to 0 and n is equal to length minus 1. Okay, so these are the endpoint indices of my list. And here is what I do. As long as start is less than end, right? As long as these 2 points haven't met, I will compute the midpoint. So in fact, I can compute midpoint like this. Okay, so it's division with no remain. I'll compute the midpoint of the start and end. So think of this example. I compute the midpoint. It's like around at 71. I'm computing the index, right? And uh, I will say, if my key is the midpoint, oh, that's amazing. When I found it, I just returned the index, the midpoint. Otherwise, if the midpoint is less than the key, what do I need to do? So the midpoint is less than the key. For example, here, I'm looking for number 80, but midpoint is 71. What should I do? I should throw away all these numbers. How do I indicate that I throw away all these numbers? I set start to be simply mid plus 1. Okay, so I move the start to mid or to mid plus 1 because I don't need the mid anymore. And otherwise, if the midpoint is too large, then I move the end toward the midpoint. So in one operation, I reduce the number of elements from n to n over 2. What happens in the next step? In the next step, I have my start and my end. Again, I compute their midpoint and I check whether I need to, maybe I already found the answer. If not, I either need to go left or I need to go right. Okay? That's the idea. So I will say these words now. If you get it, that's great. If not, then don't worry about it. Basically, in each step, if I have an array of length, if I have a list of length n, in each operation, I divide the list by a factor of 2. So what's the maximal number of operations that I'm going to do? What will be the maximal length of the while loop? Right? What's the maximal number of iterations of this while loop? So the answer is, how many times do I need to divide by 2 until, I start from n, I divide by 2, I divide by 2, divide by 2 again. How many times until I reach one element? So this is called log to the base 2 of n. And the running time is log to the base 2 of n. And maybe not exactly log, but because maybe it's 2 times log or 3 times log. But the point is that log n is much smaller than n. So the point is, if the array is sorted, then we can find the element we're looking for or declare it's not there without going through the entire list, right? In one operation, we remove half of the list. In another operation, 1/4 of the list. In another operation, 1/8 of the list. So we perform only log n operations and we compute we find the index of the array. Or we find the index of the element. Okay, and this is the code, and if you run it, yeah, you find 10 in position 3, and you find that 80 is not in the list. Okay. Okay, that was our binary search. I hope this one is clear. Uh, okay, I promised you find and count. I promised binary search. So next what we're going to do, okay, so we said, for binary search, I want my list to be sorted. But what if the list is not sorted? So what we're going to do next is we're going to learn 3 sorting algorithms: bubble sort, selection sort, and insertion sort. And I'll start with bubble sort. So here's what bubble sort does. Let me show you the code because I think the code is pretty clean for bubble sort. Okay, so here's the code for bubble sort, or let me first run it. And then, so if this is my list, then this is the list before. And after I sort it, the numbers are sorted. For example, -11 is the smallest number, and then 0, here is 0, and here is 1, and 3 appears 3 times. And 6 appears twice, right? 1 time here and 1 time there. The largest number is 55 and so on. So we sorted the list using this function called bubble sort. Let me tell you what bubble sort does. So the outer loop does the following. We have 2 nested loops. The outer loop says repeat n times. And notice I put an underscore here to indicate that the actual index doesn't matter. Okay, so simply repeat n times. What are we repeating n times? So for I in range n minus 1, so I goes from, right, I goes from 0 up to n minus 2. We take 2 consecutive elements. We take elements in position 0 and position 1. We take these 2 elements. If they're in the wrong order, right, if the element in position 1 is smaller than element in position 0, what do we need to do? We need to swap them. Here's how we swap numbers in Python. We say list in I plus 1 is equal to this pair where now we swap their values. Okay, that's all we do. And the algorithm says repeat this procedure, right? Repeat this inner loop n times, and you will get a sorted array. So maybe we'll try to convince ourselves first why this is true. All right. Well, we'll do it later. First, let's try maybe one I don't know, one example. So let's say we start with number 51428. So so here we show only three passes. Okay, but here's what we do in the first pass. We take 5 and 1. Are they in correct order? No. So what do? We swap them. 1 and 5 swaps. So this picture is from Wiki. Then we take 5 and 4. Are they in correct order? No. So we swap them. Then we take 5 and 2. Are they in correct order? No, we swap them. We take 5 and 8. Are they in correct order? Yes, they are. So we keep them. Okay. So basically we started from, from index 0 and 1. We swapped if needed. We swapped if we swapped, and so on if needed. And here's an observation. After this first pass, the maximal number will be at the very end. Why is that? We swap the first, look at maximal number sitting somewhere. I'm going to swap, swap, swap until I reach the maximal number. And this maximal now is going to swap all the way to the end, right? Every time we'll want to swap the maximal number until it reaches the rightmost point, the very end. Okay, so after one iteration, the maximum is at the very end. Okay, we'll do second pass. In the second pass, we'll have 1 and 4. Do we need to swap them? No, they're already in place, right? They're already in the right order. We take 4 and 2. Are they in the right order? No. So what do? We swap them. We get 2, 4. Okay. Next two numbers are 4, 5. Do we need to swap them? No. 5, 8. Do we need to swap them? No. This is what we get. So now the array is already sorted, but technically we need to repeat it a few more times. So we try 1 and 2. Do we need to swap them? No. 2, 4. Do we need to swap them? No. 4, 5. Do we need to swap them? No. 5, 8. Do we need to swap them? No. We stop here. Okay, so this was 3 passes. And in fact, we don't need n passes. We only need, I think, n minus 1 passes. But that's not super important. Okay, so this is our first sorting algorithm. So the algorithm says have n passes, each time doing what? Swap two consecutive numbers. And that's our algorithm. And when we run it, yeah, it actually works. Okay, so here we print A without before it was sorted, and here after it was sorted. Okay, that's algorithm 1, bubble sort. Next algorithm is called selection sort. And the idea here is the following. So we first find the smallest element and put it in the first position or in the 0 position. Then we find the second smallest and put it in the second position. Then the third smallest in the third position, and so on. So for example, if this is our list, what's the minimum of this index? The minimum is 1. So what do? We swap 1 and 4. Okay, we find minimum and we swap it with 1 and 4. Now we're looking for minimum except for this one. So what's the minimum here? The minimum here is 3. So we just keep it in place. What's the minimum of these numbers? 7, 4, 10, 8. So the minimum is 4. So what do? We swap 10 and 4, 7 and 10. Sorry. We swap 7 and 4. Swap 7 and 4 because 4 is the minimum and 7 is the index that we want to put this minimum in. Okay, 10, 8, 7. What's the minimum? 7. So 7 swaps with itself. Next, the minimum is 8. So we swap 10 and 8, and we're done. So maybe another example. Maybe this is our array. First minimum is 1. So we're going to swap 8 and 1. Okay, 8 goes here, 1 goes there. What's the minimum next? The minimum next is 3. So there's no need to swap. It's going to swap 3 with itself. What's the minimum next? The next minimum is 7. So we swap 9 and 7. And then minimum is 8. So we swap 8 with itself, and then we're done. Okay. Let's try to see the selection sort algorithm. Okay, so first I think it still works. So here's what we do. N is the length of the list. And we say for I in range n minus 1, right? So I goes from 0 up to n minus 2. So the minimal index will be the index that contains the minimum. Okay. So we set first minimum to be I. And then starting from I plus 1 up to n minus 1, if we found a smaller element, update the minimal index. In the end, if the minimal index is not equal to I, we swap list in position I with list in position mid index. Right, but we only need to do it if we do it only if needed. So we don't do it if min index is equal to I. That's your selection sort. So again, we in each iteration we are looking for the minimal element except for those that are already are already in the right place. So in the first iteration, we find the minimum and put it in list in position 0. Right? So now list in position 0 has the correct element. It has the smallest element, so we can ignore it from now. In the second iteration, we're looking for the minimal element, but ignoring the list in position 0. So whatever we find, we put it in list in position 1. So now these two, right, list in position 0, 1, have the right elements, and everything else we need to sort those. So in each iteration, in the ith iteration, we're looking for the ith smallest element. We put it in the ith position, and then we continue to the next iteration. So for each I, this one says find the minimal element and put the minimal element in the right position. Right? Put the minimal element, which is this, in list in position I. That's our selection algorithm. Okay, and the last algorithm we'll see for today is called insertion algorithm. Yeah, is that all we have for today? Okay. And it works as follows. So it's also a very natural algorithm. I mean, maybe if I were to tell you, look, you should write a sorting algorithm, this is what you would do. So here's what we have there. In the iteration I, the first I elements of the array are already sorted. And then we take the next element and try to push it in the right place, similarly to bubble sort, but we go, towards smaller elements. Let me give you an example. So we start with this way. In the beginning, we just take 8. Then we have 3. So how are we handling 3? 3, we want to push it to the left of 8, right? Because 3 is smaller than 8. Okay, so this is what we do. Then we have 9. So 9 is greater than 8, so we don't do anything. Then we have 1. How are we handling 1? So 1 is less than 9, so we swap it. 1 is less than 8, so we swap it again. 1 is less than 3, so we swap it again. And then we want to insert 7. How do we insert 7? 7 goes, swaps places with 9, swap places with 8, and then, oh, found the right place. So this is your insertion algorithm. So insertion sort algorithm. Okay, so in each iteration, we take the next item, we take list in position I, and we push it to the right place in the array, in the sorted array. And let me find insertion algorithm. Also pretty straightforward. So here's what we do. We take the element I plus 1. Okay, well, let's take element I plus 1. And we say, and we call this index j. And we say as long as j is, we don't reach the end, if we need to swap the jth element with j minus 1, we're going to swap them and then decrease j by 1. So basically we go down and go down and go down until what happens? Until list in position j minus 1 is less than list in position j, and we didn't reach the end. Right? So this condition says that our indices should not go below 0. And this condition checks that we swap the pairs of elements only as far as needed. We don't swap it too far. Right? We swap it until it finds the right place. Namely, the next element on the left is smaller than this guy. Okay, so we take this jth element, I plus 1, and we start swapping it to the left, to the left, to the left, to the left, until we find the right place. That's our algorithm. That's insertion sort algorithm. Okay, so that's uh, what I had to say about insertion algorithm. Oh, maybe another example of insertion algorithm. So let's say this is my array. I start with 100, 1 to 3. So first I swap 1 and 100, then I swap 2 and 100, then I swap 3 and 1. Right? So each time I make exactly one swap. Okay, in each iteration I make exactly one swap. Here is some homework for practice for you. So modify the insertion sort so that it sorts the list just the way we saw it, but it also returns the number of swaps that the algorithm made. So for example, here it would return 3. Okay, so the array is being sorted, but it also returns a number. So basically, if you go to the code, it will say return count or something. Okay, so you'll set here count to be 0, and then sometimes you'll update it, and after you update it, you need to return the count. Okay, so that's your goal. Here is two more tasks for you. Modify the selection sort algorithm so that it sorts the list not in the increasing order, but rather in decreasing order. And the last example is modify bubble sort so that the list in the end becomes in decreasing order, not in increasing order. Okay, that's all I have to say for today. So here's what we learned. We learned binary search and we learned tree sorting algorithm. All right, that's all I have to say for today. Thank you.